Okay, in this lecture, we're going to cover the first part of our section 1.5 material on substitution, or sometimes referred to as integration by substitution. This is something that you may have seen at the end of your Calculus 1 course, but if not, that's perfectly fine. We're going to talk about this concept in full detail here. And I'll mention before we jump into anything that in this course we're going to learn several different techniques for integrating functions. And typically something that's challenging for students is determining what technique they should use to integrate a certain type of function. So before we even introduce the idea behind substitution, let me just write a little note to the side that we would use this technique, so let me maybe say used for integrating composite functions or fractions. Or to be a little more precise, let me not say fractions, but let me say quotients of functions. So whenever you're trying to integrate a function which is either a composite function or maybe a quotient of two functions, you should immediately think of trying this method of substitution. So let's see what exactly this substitution method says, or how this works. So we'll introduce it as a theorem called the substitution rule, which says if we are looking at integrating a function which is a composite function, let's say something of the form f of g of x, then we would choose a new variable u to be our inner function. So we're going to name the inner function in this composition, g of x, some new variable u. And let's suppose that this function is differentiable. So our goal is to take the integral involving the composite function f of g of x in terms of x and rewrite it in terms of an integral involving u. So if we let u equal g of x, then this composite function f of g of x becomes simply f of u. Now, one thing that we require, or that we need in order for this method to work, is some other term in our integrand to involve the differential of u, or the derivative of this inside function, g prime of x. Now, the reason that this works is this last expression, g prime of x dx, is equal to the differential of u. So recall here, if u is chosen to be g of x, that means that the derivative of u with respect to x would be the derivative of this g function, that is g prime of x. So it follows that the differential of u is equal to g prime of x times the differential of x. Recall that definition of differentials from your Calculus 1 course. So this term that we had in the original integral involving x, which g prime of x dx, is just the differential of u. And so this new integral only involves the variable u, and typically this new integral in terms of u is something that's much easier to integrate. That is much easier to find an antiderivative of. The first step of this process involves choosing the value for u. So I mentioned here that in general, typically we would choose u to be that inner function in our composition of two functions. Or to be a little more precise, we choose u so that the differential of u will be some factor of the integrand. Now, in the vast majority of cases, we're using substitution to integrate composite functions, and u is chosen to be the inner function in that composition. So let's look at some examples to illustrate how this method works. So in this next example, we'll go through a bunch of parts, and we're asked to evaluate the given indefinite integral. So in part A, we have the integral of 2x squared times the square root of x cubed plus 1. So when I look at this integral, I immediately think of using a substitution because I see that part of my integrand involves a composite function. This isn't just the square root of x, but the square root of a function of x cubed plus 1. So again, as you're going through the course, something to keep in mind is you should immediately think of using a substitution anytime you're integrating a composite function. So in this case, I'm going to make a choice for u. And typically we choose u to be the inside function in our composition. So in this case, x cubed plus 1. Now, the next part of this process is we need to solve for the differential of u. So a good way to go about doing this would be the following. Once we choose u, let's find the derivative of u with respect to x. So here, if u is x cubed plus 1, then our derivative would be 3x squared. And now I want to try to solve. Let me work a little further and then I'll explain my thought process. So in general, our goal is to take this integral that we had in terms of x and rewrite it in terms of u. So we now have the integral of 2x squared times the square root of u. So we replaced this x cubed plus 1 with u, and then on the end we have the differential of x. So my integral now involves both the variables x and u, and I want to write it only in terms of u. So I need to change this differential of x on the end into du. So let's think about how to do that. If we look back at our expression that we found for the derivative, du dx, that implies that the differential of u is equal to 3x squared dx. And so solving for dx, we have du over 3x squared. So let's take that expression for dx and substitute it into our integral. So we now have the integral of 2x squared times the square root of u, and then dx is equal to du divided by 3x squared. So now we see that these x squared terms in the numerator and denominator will cancel one another, and we're left with the following. We have a 2 divided by 3, or 2/3, and that constant I can bring out in front of my integral, and then I'm still left with the square root of u du. So I've, by making this substitution, or this change of variable, I've got an integral in terms of u, which is much easier to evaluate than the one I started with. So let's think about this. To integrate the square root of u, or u to the 1/2, well, we have a constant 2/3, And then using the power rule to find our antiderivative, well, we take u to the 1/2 and we add 1, so we get u to the 3/2. And then we divide by 3/2. But now dividing by 3/2 is equivalent to multiplying by the reciprocal, 2/3. And now that I've found my antiderivative, I can include a constant of integration on the end. So simplifying a little bit, we have 2/3 times 2/3, or 4/9, u to the 3/2 power, plus c. But one thing that we want to do when we're using this substitution method is express our final answer in terms of the same variable that we started with. So in the statement of the problem, in part A, the function that we were integrating involved x and not u. So we want our final answer in terms of x. So to get it, we're going to take whatever we called u, in this case x cubed plus 1, and substitute it back into this function that we found as our antiderivative. So we have 4/9 times u, which was x cubed plus 1, all raised to the 3/2 power, and then plus some constant c. So we have the following expression for our antiderivative of that composite function. And recall that one way you can always check your work when you're finding antiderivatives or indefinite integrals, if you take the derivative of this function, you should get back the integrand, the function that you were integrating. So it's pretty straightforward to check here that we do indeed get back the function that we were integrating if you take the derivative of this answer, making use of the chain rule. So let's look at another example. We're going to do a lot of these to familiarize ourselves with this procedure. So in the next example, part B, we're integrating secant squared x divided by the square root of tangent x plus 2. So again, as soon as I see this integral, I notice that I have a composite function as my denominator. It's the square root of tangent x plus 2. So that should immediately make me think of a substitution. And my first step in the method of substitution is to choose a value for u. So here, u I will choose as tangent x plus 2. That is the inside function in my composition. And from here, we have the differential of u, du, would be the derivative of tangent x, which is secant squared x, plus the derivative of 2, which is 0, times the differential of x. So, as with our previous example, part A, we need to solve for dx, and we're left with du over secant squared x. Okay. So now, looking back at our original integral, which was secant squared x over the square root of tangent x plus 2 dx, we want to rewrite this in terms of u. So let's take a look at it. So our denominator was the square root of tangent x plus 2. Well, that's what we called u. So we now have our denominator as the square root of u. And then we had a numerator of secant squared x. And then the differential of x, dx, we solved for as du divided by secant squared x. So we see here that the factor of secant squared x in the numerator and denominator cancel one another. And we're left with the integral of du over the square root of u. Now, in order to find an antiderivative for this function, we would most likely rewrite it. So 1 over the square root of u is the same as u to the negative 1/2 power du. And doing this allows us to use the power rule to find our antiderivative. So we would add 1 to the exponent, giving us u to the positive 1/2. And then we would divide by 1/2, which is equivalent to multiplying by 2. And at this stage, once I've found my antiderivative, I can add an arbitrary constant to get the most general antiderivative, or the integral. And as with our previous example, I'm not quite done. So here my original integral was in terms of the variable x, so I want my final answer to be in terms of that same variable. So let's substitute u back in. So we had 2 times u, which was tangent x plus 2 to the 1/2 power plus c. Or if you prefer, this is the same as 2 times the square root of tangent x plus 2 plus c. So just 2 different notations there, but recall the 1/2 power is the same as the square root of that function. All right. So let's look at some other ones. In these next few examples, we'll have some functions involving exponentials. So in part C, we need to evaluate this indefinite integral. And when we're looking at it, we see that it involves a composite function. Not just e to the x, but e raised to a function of x. And as soon as I see that composite function, I'm immediately thinking of a substitution. Now, once I know I'm using a substitution, my first step is to choose u. So I'm going to choose u as the inside function in my composition, in this case, 1 minus 3x squared, which means that the differential of u is negative 6x times the differential of x. And as with our other examples, we're going to solve for dx so that I can replace my dx by something involving du when I actually make the substitution. So to solve for dx here, I would take du and divide by negative 6x. All right. So let's take a look at what we have. Now our integral that we started with was x e to the 1 minus 3x squared dx, which we're going to rewrite in terms of u. So we have x e now to the u power, since the exponent, 1 minus 3x squared, is what we were calling u. And then this factor dx that appeared on the end, well, we solved for dx in our earlier work. We found it is du divided by negative 6x. So let's see what we're left with. So after making our substitution, this x and the division by x that we got from our dx term will cancel one another. And we're left with a constant factor of 1 over negative 6, which I'm going to pull out in front of my integral as a negative 1/6. And then we still have within the integral e to the u du. So this new integral that I have in terms of u is, of course, much easier to handle. We know that we have a constant negative 1/6, and the antiderivative of e to the u is e to the u. And at this stage, once I found my antiderivative, I can include an arbitrary constant to find my integral. That is the most general antiderivative. And again, in our last step, we want to express our final answer in terms of the variable x. So the expression that we had for u, 1 minus 3x squared, we're going to substitute back in. And we have a negative 1/6 e to the 1 minus 3x squared plus c. And again, for all of these problems, we can always take the derivative of our solution and make sure that we get back the original function that we were integrating. All right. So let's look at some other ones also involving exponentials. In part D, we have the integral of e to the 1 over x divided by x squared dx. So again, when I'm looking at this, I recognize that the numerator is a composite function. It's not just e to the x, but e raised to the 1 over x power, or e to a function of x. So as soon as I see that composition, that immediately makes me think of a substitution. And so let's start by choosing an expression for u. So as with most of our examples, when we have a composite function, u is chosen as the inside function, in this case 1 over x. And so the differential du would be negative x to the negative 2 power, or negative 1 over x squared, times the differential of x. And as with all of our previous examples, we need to solve for dx. So here, to solve for dx, I could multiply both sides by a negative x squared. So I have negative x squared times du is equal to dx. So now let's rewrite our given integral, which was e to the 1 over x squared dx in terms of u. So we have the integral of e to the u divided by x squared, and then times dx. Now we solved dx, or solved for dx, as negative x squared times du. So we can see here that our x squared term in the numerator and denominator cancel nicely, and we're left with just a factor of negative 1, which I can pull out in front of my integral. So I have the negative integral of, well, let's see what we're left with. We just have e to the u du. And we know how to find the antiderivative of e to the u. So we have our negative out in front. The antiderivative of e to the u would be e to the u plus c. And as with our earlier examples, we want our final answer in terms of the variable x. So let me substitute u back in, and I have negative e to the u, which was 1 over x, plus c. All right. So let's look at another one. In part E, we have the function e to the sine of 2t times cosine of 2t dt. So again, when I look at this one, what is it that immediately makes me think substitution? Well, it's this first factor. The first factor in my integrand is a composite function. In fact, it involves a couple of compositions. We have e, not just to the sine of t, but sine of 2 times t. So as soon as we see this, we should think of using a substitution. And so I'm going to choose u as the inner function in my composition. In this case, sine of 2t. So here, as soon as I have made my choice for u, I'm going to try to find the differential of u. Now in this example, u is still a composite function. It's sine of 2t. So when I'm finding my differential du, I'm going to have to make use of the chain rule. So we start by differentiating the outer function. So the derivative of sine of stuff would be cosine of stuff, in this case cosine of 2t, and then we have to multiply by the derivative of the inside function. And here the derivative of 2t is 2. So our differential du would be 2 cosine of 2t dt. And I need to solve for the differential of t. So to do it, I could take du and divide through by 2 cosine of 2t. So let's see what this buys us. If we go back to our original integral, which was e to the sine of 2t times cosine of 2t dt. If I rewrite this in terms of u, I have the integral of e to the u times cosine of 2t, and then our differential dt on the end we solved for as du over 2 times cosine of 2t. So after we've made this substitution, we can see that this factor of cosine 2t in the numerator and denominator will cancel one another, and we're left with a constant factor of 1 over 2, or 1/2, which we can bring out in front of our integral. And then we're just left with e to the u du, and we know how to find an antiderivative of e to the u. It is, well, we have our constant 1/2, and the antiderivative of e to the u is e to the u plus some constant c. So again, in our last step here, we want to get our final answer in terms of the variable t that we started with. So we will have a 1/2 e raised to the u, which was sine of 2t, plus c. All right. So working through several of these examples, we're starting to see how this process works more generally. As soon as we see that our function involves a composite function, we should try a substitution. We start by choosing u, which is typically chosen as the inner function in that composition. Then we have to find its differential and solve for dx or maybe dt, whatever differential was given in the original integral. And then by making our substitution, we get hopefully an integral which is easier to handle than the one we started with. So let's look at some other examples. Here in part F, we have the integral of secant squared of natural log x over x dx. So again, when I look at this, what is it that makes me think substitution right away? Well, I recognize that my numerator is a composite function. So I know I'm going to try a substitution here, and my first step is to make a choice for u. So u, I'm going to choose as the natural log of x here, since that is my inside function in that composition, in which case the differential of u is 1 over x times dx, the differential of x. And so, solving for dx, I could multiply both sides of that equation by x, and I would have x times du. So now, looking back at our original integral, we have a numerator of secant squared of u divided by x, and then we're multiplying by dx, which we solved for as x times du. So we see here that the x in our numerator and denominator cancel, and we are left with the integral of secant squared u du. To integrate secant squared, well, there's a few ways we could do it. The easiest approach is to recall that the derivative of tangent of a variable is secant squared of that variable. For instance, a derivative of tangent x would be secant squared x. So the antiderivative of secant squared u is simply tangent u plus some constant c. And as with our earlier u substitution examples, we want our final answer in terms of the variable that we started with, in this case x. So we're going to substitute u, which was the natural log of x, back into our antiderivative. So we've got the following. All right. So let's look at another example. In part G, we have x times cosine of 2 minus x squared. And again, as soon as I see this composite function in my integrand, I'm immediately thinking of using a substitution. So my first step in a substitution is to make a choice of u. And here I'm going to choose u to be the inner function in my composition, in this case 2 minus x squared. And then we calculate the differential of u, which would be negative 2x dx. And so solving for the differential of x, we could divide both sides of that equation by negative 2x, and we have dx is du over negative 2x. So let's look back at our original integral. That is x times cosine of 2 minus x squared dx. And we're going to rewrite this in terms of u. So we have the integral of x times cosine of u, is what we were calling that inner function. And then on the end, we have the differential of x, which we just solved for, as du divided by negative 2x. So we're left with an x divided by x, canceling one another. And we have a constant factor of 1 over negative 2, or negative 1/2, which we can pull out in front of our integral. And then we just have the integral of cosine u du. And we know how to find the antiderivative of the cosine function. The antiderivative of cosine u is positive sine of u plus c. And as with our earlier examples, we want to substitute our expression for u back into our function. So we have a negative 1/2 sine of 2 minus x squared plus c. Okay. So here, these last couple of examples involving trig functions, but the general process is the same. As soon as we see those composite functions, we think substitution and make our choice for u. So these next two examples are going to illustrate something that's a little tricky when we're using a substitution. So for certain functions, after we make a substitution, it might appear that we get stuck, that our differential terms don't end up canceling each other nicely, in which case we have to do a little extra work in order to rewrite our integral in terms of the variable u. So let's look at a couple of examples of this. Starting with in part H, we have the integral of x cubed times the square root of x squared plus 2 dx. So again, when I'm looking at this integral, I'm immediately thinking of using a substitution because my function involves a composite function. It's the square root of a polynomial. So once I know that I'm going to try a substitution, my first step is to choose an expression for u. So as with all of our previous examples, I'm going to choose u as the inner function in my composition, in this case x squared plus 2. And then we find the differential of u, which would be 2x times dx. And so solving for dx, we would have du divided by 2x. So let's see what happens here. Now our original integral, which was x cubed times the square root of x squared plus 2 dx, can now be rewritten as the integral of x cubed times the square root of u, and then the differential dx on the end we solved for as du over 2x. So let's see what happens here. Now we run into a little bit of trouble because our remaining x terms don't cancel each other exactly as they did in our previous examples. So in particular here we have an x cubed, which is being divided by x to the first. So I can cancel one factor of x on top and bottom, but I'm stuck with this x squared term. And let's see what else. So the constant factor that I have in this case is 1 over 2, or 1/2, which I'm going to pull out in front of the integral. And now after canceling our one factor of x, we're left with x squared times the square root of u du. So when we first rewrite this, it might seem like this didn't work out because this x squared term still remains. We're stuck with it. It didn't cancel exactly with an x squared in the denominator as with our previous examples. So what can we do here? Well, if we're a little bit clever, we can look back at our choice for u. So here we were calling u x squared minus 2, and the term that I'm stuck with is x squared. So using our choice for the substitution, well, let's just solve for x squared. So a little scratch work up here. If we subtract 2 from both sides, we find x squared is equal to u minus 2. So this x squared term that I was left over with is just equal to u minus 2 by making use of our substitution. So let's rewrite it in that form. We have a constant 1/2 out in front. X squared, we just said, is equal to u minus 2. And then after x squared, we were multiplying by a square root of u du. So now we're almost ready to integrate this. We've got everything written in terms of just the variable u. But in order to integrate this, well, we've got a product of two functions. As of right now, we don't know how to integrate products in general. But what I could do is take this factor of square root of u and distribute it to each term in u minus 2. So that is expand this function. And we have 1/2 of the integral of, so for our first term, we're taking the product of u and the square root of u. So that is u to the first times u to the 1/2, which would give us u to the 3/2 power. And then minus 2 times the square root of u, or if you prefer, u to the 1/2 power, du. So now we're ready to integrate this function by using the power rule for each term. So out in front we have a constant 1/2, and we're multiplying by the antiderivative of u to the 3/2 would be u to the 5/2. So we add 1 to the exponent, and then we divide by 5/2, which is equivalent to multiplying by the reciprocal, 2/5. And then we're subtracting. We have 2u to the 1/2 power. So adding 1 to the power, we get u to the 3/2 power. And then we're supposed to divide by 3/2, which is equivalent to multiplying by 2/3. Now here we already had a constant 2 out in front. So taking 2 times that 2/3 will give us 4/3. And at this stage, once I've found my antiderivative, I can include the plus c for my constant of integration, and we're almost done. So let's simplify just a bit further. So here, taking my constant factor of 1/2 out in front and distributing to each term, I have a 1/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. And in my very last step, I'm ready to substitute the expression for u back into my answer. So recall that we were letting u be x squared plus 2. So substituting back in, we have 1/5 of x squared plus 2 to the 5/2 minus 2/3 of x squared plus 2 to the 3/2 plus c. So this would be our antiderivative of that function. So this example, part H, is illustrating that even if you use a substitution, you might get stuck with some term involving x after you've made your substitution. In this case, we were stuck with an x squared term. And in that case, we can still try to make the substitution work by looking back at our choice for u and solving for that term that we're left with. In this case, we solved for x squared in terms of u, and then we were able to write our entire integrand just in terms of the variable u instead of x. So that's something that comes up with some of these substitution problems that can be a little bit tricky. So let's look at another one of these. In part I, we have the integral of x to the 5th over x cubed plus 1 all raised to the 4th dx. So again, when I'm looking at that integral, the fact that our denominator is a composite function immediately makes me think of using a substitution. So let's start by making our choice for u. So here I'm going to choose u as the inside function in that composition, that is x cubed plus 1, in which case the differential du is 3x squared dx. And so dx is then du divided by 3x squared. So going back to our integral, we had x to the 5th over x cubed plus 1 all to the 4th dx, and we're going to rewrite this in terms of u. So we have a numerator of x to the 5th over u to the 4th power, and our dx term on the end is equal to du over 3x squared. So let's see what we're left with. So I'm going to start with the constant term. We have a constant factor of 1 over 3, or 1/3, which I can bring out in front of the integral. And let's see which terms are going to simplify. So we have here an x to the 5th divided by x squared. So I can cancel 2 powers of x on top and bottom, and I'm left with x cubed divided by u to the 4th du. So as with our previous example, in this case we get stuck with this x cubed term in my numerator. So what can we do? Well, if we look back at our choice for the variable u, we saw it was x cubed plus 1. So to solve for x cubed, we could just subtract 1 from both sides. X cubed is then u minus 1. So our numerator for this new integral, which was x cubed, we can rewrite as u minus 1. It's all being divided by u to the 4th, and then we have our differential du on the end. So now what we're left with in terms of u is an antiderivative of a quotient. Thus far, we don't really have a nice method for handling antiderivatives of quotients in general. So one way that we could go about handling this is to split this fraction into two pieces. Our numerator is u minus 1 all over u to the fourth, which we can rewrite as u over u to the fourth minus 1 over u to the fourth du, which gives us a 1/3 integral of 1 over u cubed minus 1 over u to the fourth du. And in order to find antiderivatives for each of these terms, we probably prefer to write them as follows. So 1 over u cubed is the same as u to the negative third minus 1 over u to the fourth is u to the negative fourth du. And at this stage, we're ready to find our antiderivative. So we have our constant 1/3 out in front times the antiderivative of u to the negative 3 would be u to the negative 2 divided by negative 2. So let me rewrite this a little bit. And then the antiderivative of u to the negative fourth would be u to the negative third divided by negative 3. But since we were subtracting that term, these two negatives are going to cancel. We'll have a positive u to the negative third over 3 plus a constant c. So let's simplify a bit further here. So I'm going to start by grouping my constant terms. So I had my 1/3 out in front, which I'm going to distribute to each of these terms. So for my first term, I have a 1/3 times a negative 1/2, which would give me negative 1 over 6. And then this u to the negative 2 term is the same as division by u squared. And distributing the 1/3 to our second term, we have 1/3 times 1/3, or 1/9. And then this u to the negative third is the same as division by u cubed, with my plus c on the end. So in my very last step, I'm ready to substitute our expression for u back into our answer. So here I've got a negative 1 over 6 times u, which was x cubed plus 1 squared, plus 1 over 9 times u, which was x cubed plus 1 quantity cubed, plus c. So finally, we have this expression for our antiderivative. So we see in these last two examples that in some cases our substitution works out a little messier if we get stuck with some leftover term involving x, because we have to then solve for that resulting expression in terms of x using the variable u, and that can often give us an integral involving u, which is a little more tedious to handle. So let's look at a few more examples to finish up this lecture. So I mentioned at the beginning of this section that we're using substitution to handle integrals of composite functions or quotients of two functions. So these last few examples are going to illustrate how a substitution can be used to handle a quotient. So a typical example might be something like the following. In part J, we have an integral of a rational function, that is the quotient of two polynomials. And we see that it doesn't involve a composition, so it's not obvious immediately that we should try a substitution. But if we keep in mind that substitution can be used to handle quotients sometimes, we could do the following. So when we're trying to integrate a quotient using substitution, we're typically going to choose u as the denominator. So for this rational function, let us try a substitution where u is taken as the denominator, x cubed minus 3x plus 1. Now the rest of this method works the same as what we've been doing. Here we're just making a different sort of choice for u. Instead of the inner function in a composition, we're choosing it as a denominator of some quotient. Now our next step in this process of substitution is to find the differential of u. So here we would have a 3x squared minus 3 times dx. And so solving for dx, we would have du over 3x squared minus 3. All right, so let's take a look at what this gives us. Our original integral, which was x squared minus 1 over x cubed minus 3x plus 1 dx, we can rewrite as the integral of x squared minus 1 over u, and then dx we found was du over 3x squared minus 3. So at first glance it might not appear that this works out very well, but if we look at these terms in the numerator and denominator, we see that this expression, 3x squared minus 3, is just 3 times x squared minus 1, the factor that we had in the numerator. So if we were to factor out that 3, we're left with exactly x squared minus 1. So canceling a factor of x squared minus 1 in the numerator and denominator, we are left with a factor of 1 over 3, or 1/3, which we can bring out in front of the integral. And our numerator is then just du, and we're dividing by u. So this new antiderivative that I have in terms of u is easy to handle. We have a 1/3, and the integral of 1 over u is the natural log of absolute value u plus c. And again, with this method of u substitution, once we have found our antiderivative, we're going to substitute the expression for u back into our answer. So we have 1/3 natural log of the absolute value of x cubed minus 3x plus 1 plus c. So this example illustrates how a substitution could also be used to handle an integral of a quotient of two functions. So let's look at another one of these. In part K, we have the antiderivative or the integral of tangent x. So we know how to handle, or we know the antiderivatives of sine and cosine. The antiderivative of sine x is negative cosine x, and the antiderivative of cosine x is sine x. But what about our other trig functions? So for tangent x, let's think about how we can use a substitution to find our antiderivative. So we are comfortable with working with the sine or cosine functions. So rewriting tangent x in terms of sine and cosine, well, tangent x is the same as sine of x over cosine of x. So rewriting it in this way, we now recognize this as the integral of a quotient of two functions, and that might make us think of a substitution. So here, let's make a choice of u. Now we mentioned for fractions, or for quotients, typically a good choice for u is the denominator. In this case, cosine of x. In which case, du is negative sine x dx. And so, solving for dx, we have du over negative sine x. So let's look back at our integral. We were looking at the integral of tangent x, which we wrote as sine x over cosine x. So this is now the integral of sine x divided by cosine x, which is what we call the u, and dx we found to be du over negative sine x. So we see here that the sine x factor in the numerator and denominator cancel. We're left with a constant factor of -1, which we can bring out in front of our integral. And we then have du over u. Now we know how to handle this antiderivative. We have a constant of -1 out in front. The integral of 1 over u is the natural log of absolute value u plus c. And again, we're going to substitute u back into our answers. We have a negative natural log of u, which was cosine of x, plus c. So this is the antiderivative for tangent x. It's the negative natural log of absolute value cosine x, which we've shown by using a substitution. Now, if you look in some other textbooks or online resources, and you are looking at the antiderivative of tangent x, you'll sometimes see it written as the natural log of the absolute value of secant x plus c, which seems like it might be a different answer than what we found here, but these are actually the same function. And the way to justify this is by using properties of logarithms. So here, recall that if you have a constant in front of a logarithm, like this constant -1, you can bring that constant inside the logarithm as a power. So in other words, when we had the negative natural log of cosine x, that's the same as the natural log of cosine x to the -1 power, but raising a function to the negative first power is the same as taking its inverse. So this cosine of x to the negative first is the same as 1 over cosine of x, and 1 over cosine of x is exactly secant x. Okay. So a little justification, you can use either of those formulas because they are indeed the same function. Now to handle cotangent, cotangent works very similarly. You would write cotangent as cosine of x over sine of x, and then use a u substitution where u is sine x. I leave it to you, if you're interested, to find the antiderivative of cotangent x. It might pop up from time to time in our course. And then in our last example for today's lecture, part L, we'll talk about the antiderivative of the secant function. So now we know how to handle sine x, cosine x, tangent x, and cotangent x, but what about secant or cosecant? So these antiderivatives are a little tricky. They work by using a substitution, but we have to be a little clever in rewriting our function in a way so that a substitution works. So here I have the antiderivative of secant x, and what we're going to do is multiply this function, secant x, by 1, so that we're not changing the function, but the way that we're going to write 1 is a little bit clever. So I'm going to multiply this function by secant x plus tangent x over secant x plus tangent x. So I've just multiplied by 1. I haven't changed the value of our function. It's still equal to secant x. But let's see what this buys us. So by distributing this secant x term through to the numerator, we have a numerator of secant x squared plus secant x times tangent x. And it's all being divided by our secant x plus tangent x dx. So it seems at first like we're making this much more difficult, but here we're integrating now a quotient of two functions. So let's try a substitution where u will be chosen as this denominator. So I'm going to let u equal secant x plus tangent x, so that the differential of u is equal to, well, the derivative of secant x is secant x times tangent x, plus the derivative of tangent x is secant squared x, and then we're multiplying by the differential dx on the end. So let's see what this gives us. We have the integral of, well, our denominator is what we were calling u, and let's look at the rest of this. Our numerator was given by secant squared x plus secant x tangent x times dx. Now where else does that appear? Well, we have it right here, secant squared x plus secant x tangent x all times dx. This is just equal to du. So our entire numerator simply reduces to du, and now the antiderivative of 1 over u du is simply the natural log of absolute value u plus c. And so to get our result, we simply substitute u back in. We have the natural log of absolute value secant x plus tangent x plus c. So this is an expression for the antiderivative of secant x. We see here that to derive this formula, we can make use of a substitution if we are very clever in the way we manipulate our function. I'll mention that this integral will come up a few times over the course of the semester. So you can either evaluate the integral as we've shown here using a substitution, or what most students prefer to do is simply memorize this formula for that antiderivative. So in your lecture notes, you might put a little star by this part to draw your attention, and I would encourage you to memorize this expression for the antiderivative of secant x.